Yeah, so I'm going to spend about 15 minutes on historical stuff on the slides, and once we get through that, I will switch to the blackboard. Yeah, so edit distance. Anybody not know what edit distance is? Okay, so we'll do this very fast, right? Elementary operations on a string, character deletion, insertion, substitution, and then the Levenshtein distance between two strings is the number of elementary operations to change x to y. It is an exercise that's symmetric. You can also think of it, and we'll think of it sometimes as you don't allow insertions, you only allow deletions, and then you want to, or substitutions, and what you want to do is change both x and y. So you can either make substitutions on either x or y, or you can do deletions on either x or y, and then you want to make them the same. And all of those measures give you exactly the same measure. Okay, so when you teach undergraduate algorithms, one of your first examples of dynamic programming is this problem. Runs in order n squared time. If you run, there are algorithms which if you run the algorithm, then the running time depends on the instance, and in particular the distance. So there is an algorithm of Buchanan which runs in order nk time. That's still n squared, of course, because the distance can be as large as n. And then there's another one in the same vein, which is, you'll see is better, but it's order n plus k squared time. So notice in particular, if the distance is just square root of n or less, then this is linear time. Okay, now for unrestricted, no assumption on the instance, the best algorithm is that. So it's essentially saving a log squared n factor. Mazik and Patterson had shaved off a log factor. And the recent result, relatively recent result of Backers and Indig, suggested, it sort of indicates why it's hard to get below n squared, because if you can get an n to the 1.99 algorithm, then you can re-engineer your algorithm to solve SAT in better than 2 to the n time. Okay, so you can map an arbitrary instance of SAT into a very large instance of edit distance of size 2 to the n over 2. And when you do that, if you could do this in subquadratic time, then you'll get a sub-exponential time algorithm for SAT. And there's another result of, along these lines, shaving an arbitrarily large polylog factor would imply that next doesn't have non-uniform NC1 circuits. So you would get a circuit lower bound that we believe is true, but we don't know how to prove. Okay. So now for approximation algorithms, well, here's what's, so the left-hand side is the factor of the approximation.
So you just want to find, you actually want to find the sequence of edits.
Well, that's a good question. I mean, when we talk about the approximation algorithm, it's find, just a number.
That's the number.
Let's say an upper bound on the edit distance that's within a certain factor. And then there's another question. And for some of these algorithms, it's not hard to see that that the algorithm gives you the sequence of edits, and some of them it doesn't. And for ours, you can actually read off the sequence that will give you
But for us, approximation algorithm is just approximate the number of edits needed with
just approximate the number of edits needed. Okay, so you're really using, think of this, the killer app for this is DNA databases, right? You've got, lots of DNA strings, and you want to compute and you're using edit distance as your measure. One could argue, and it's not clear that edit distance is the right measure, but okay, that's, all right. So there are a bunch of algorithms. You'll see that the runtime of all these algorithms is linear or close to linear. All right, and the first one, well, the factors initially were not so good. So a square root of n factor. Okay, and in fact, it's not hard to use. We had that order n plus k squared algorithm. Okay, so if you run that algorithm for a linear amount of time and the edit distance is less than square root of n, you'll get it exactly. And otherwise, you just output n, and then you know you're within a square root n factor. So that's that one. Okay, and then there were some improvements, n to the 2/7, n to the 1 minus epsilon over 3. Then there was an interesting n to the 1/3 algorithm where the running time was actually n to the 1/3. So you get an approximation factor of n to the 1/3, and you get but the running time is sublinear.
This is like a property testing type.
Yeah, that's right. Then there was Andoni and Onak that got a sub-polynomial, so less than n to the epsilon for any epsilon that runs in close to linear time. And then the best previous, which was this log n to the 1 over epsilon, which runs in order n to the 1 plus epsilon time. All right. And I'll mention that also in the Andoni, Kraut-Gamma-Onak paper, they established that if you run in, let's say, n to the 0.99 time, so truly sublinear time, then there are information theoretic limitations which are going to keep you from getting better than a log n factor. Okay. Whoops. Okay, so now as far as hardness, well, okay, or at least evidence that it might be hard to find approximation algorithms. But there was the thing I mentioned, which is getting truly sublinear time is hard. Here, Budenbacher's had a paper where they showed that if you could get a 1 plus little o1 approximation in subquadratic time, then this would imply some circuit lower bounds that we don't know how to prove.
Do you remember which circuit lower bounds?
It's kind of similar to the one I mentioned before, but I mean, I don't know it off the top of my head.
I might see one lower bound for next or something.
Yeah. Okay. We'll also mention that, so there's a restricted case, the Ulam distance of permutations, which is essentially, I give you 2 permutations of 1 through n, and you allow insertions and deletions, but no substitutions. The substitutions actually just introduce a factor 2 additional, meaning you can always replace a substitution by an insertion followed by a deletion. So if you don't care about factors of 2. So Andoni Nguyen got an algorithm which runs in square root n plus n over k.
So
Yeah.
the restricted model, so what's really the restriction then?
Oh, the input. So the input is 2 permutations as opposed to
Arbitrary restriction.
just arbitrary strings. Okay. Now in this case, so the running time of their algorithm is root n plus n over the distance. So here the distance appears in the denominator. And the reason for that is that there's this needle in a haystack problem. if I just want to tell the difference between the two strings are identical versus that they differ in one place, then if you just use sampling, which is what you just won't find it. So you need, if you've got only k differences, you need n over k time to even find any difference. Okay. And so they got a constant factor, a large constant factor, and then follow-up work, essentially refining their techniques and combining it with something else. We got a 1 plus epsilon factor approximation for any epsilon in the same running time. Okay, and then there was a recent quantum approximation algorithm for edit distance. And they got a 3 plus epsilon factor in running time subquadratic. Okay. And I'll say something a little bit about the relationship between the quantum algorithm. There is some connection between the algorithm I'll describe and the algorithm that they did, where at some point there's a problem that needs to be solved, and they use Grover search to solve it. And we have a different way of solving that problem. Okay. All right, so here's the theorem. There is a randomized algorithm, edit distance UB for upper bound, that on input strings xy of length at most n runs in time order. The tilde, I can't get the tilde over the O in PowerPoint. So O tilde of n to the 12/7, and outputs an upper bound on the edit distance that with high probability is at most c, the constant times the edit distance for some fixed c. Well, our c in the paper is 3,360, but you will see, if you care, you will see that there are loads of places. We just are very cavalier about factors of 2, which we gave up tons of factors of 2 along the way. So this can be greatly reduced. What's that?
The biologists will be very excited.
Yeah.
But the previous one was just log n, the best.
Log n to the 1 over epsilon. Well, log n to the 1 over epsilon.
But certainly not lower than log n.
What's that again?
In subquadratic time, it was nobody knew how to get better factor of approximation.
Right.
Than log n.
Yeah. Okay. And now, so Alex Andoni just put out a couple of weeks ago something which takes our method. So you'll see what we do is pretty simple. I hope I'll be able to explain everything. I won't give you all the equations, because they're all things that you can do as exercises, really. You take the basic method and he improves the runtime to order n to the 3/2. Michal and I are working on a paper which, well, I put November. That's hopeful. There's a stock deadline, so we're hoping to meet it. Okay, so we can get a constant factor approximation in order the n plus 1, but there's a catch. The catch is that our algorithm only works on inputs that have relatively high edit distance. What happens actually is our algorithm will have an additive approximation of this. Okay, so it'll be a constant factor approximation plus an error of this. And I think that's an artifact of our current algorithm. I expect that either we or somebody else will get rid of that. So I really do think that there will be a constant factor approximation in n to the 1 plus epsilon time. Okay. All right, so again, that's just, so let's go back. That's the result I'm talking about here, n to the 12/7 time. And here's the main lemma. So this is for people who do approximation algorithms. We reduce it to what's called a gap problem. And this is just a completely standard reduction. So there's a randomized algorithm gap upper bound, which takes as inputs strings xy of this some length n, and a parameter theta in this range n to the minus 1/5 to 1. Okay. It runs in time n to the 12/7 times this theta parameter, so that's better than, but theta, well, you'll see what role theta plays. It outputs an upper bound u on the edit distance, such that if you run it on instances whose edit distance is small, where small is defined by theta, then the output is guaranteed to be at most. So notice here the output is not guaranteed to be at most a constant multiple of the true edit distance. It's just a constant multiple of this 8. So what you're really doing is, it's called a gap problem, a gap algorithm, because what I'm able to do with this algorithm is, for the particular theta, I can distinguish between my algorithm will distinguish between those instances which have edit distance less than theta n or greater than 840 theta n. So there's this particular gap, and we will distinguish it. Okay. Once you can do that, then it's a standard kind of binary search thing to actually use this thing as a black box. So, I mean, I go through the, yeah. So we also need this exact algorithm. So we start by running the exact algorithm for n to the 12/7 time. Okay. So either this thing terminates, in which case we get the exact edit distance, or it doesn't terminate. If it doesn't terminate, well, then we know the edit distance is big. We know it's bigger than n to the 6/7. Okay, so now we apply the gap algorithm for different powers of 2, and you output the minimum output of all the runs of your gap algorithm, and then you just check this claim is true, that this minimum of all the runs will give you an output where the edit distance is between x, y, and 16. Now, I should say, so I said that our algorithm pays a factor of 3360, which is twice this. And the thing I hid from you is that one of the first reductions we do is we reduce to the case that x and y are the same length. And that costs another factor of 2, which you can, it's easy to see. Yeah?
Can you explain step 3?
Yeah, so if this algorithm is guaranteed to halt in this time if the edit distance is k. So if we run it for n to the 12/7 time and it doesn't halt, then we know that
Why is that bound n to the 6/7?
the square root of n to the 12/7. Okay. Other questions?
The alphabet doesn't matter to you at all?
No. All right. And now I'll just, my last slide is this picture. So is this one, which is, so, this is how you map edit distance to a graph. Okay, it's a shortest path in a graph. Again, many of you may have seen this, but so what I do is I think of the horizontal axis as labeled by the symbols of the x string, and the vertical axis as labeled by the symbols of the y string. Okay, and the node corresponds to a way of matching this substring to this substring. So if I'm looking at this node, it's kind of a path in this graph will correspond to a way of matching this string to this prefix. Now, if I want to get the shortest path from here to here, then what happens? Well, I can either, the last step that I do, so let me look at the last symbol of each one. I could either do a substitution. That's like moving from this edge, from this node to this node. Or I can, so now I'm thinking of it as I either delete a symbol from X or delete a symbol from Y, as that's what I mentioned. So if I delete a symbol from X, then this corresponds to, I find the best way of matching these two, and then I just move to here and I pay 1 for doing that, or I do the same thing going this way. All right. So what happens then is that if you want to know what is the best way, the cheapest way to match this guy to this guy, it's just the length of the shortest path in this graph. Okay, and
the strings are not given. This is just a template. I mean,
this is a template, right? You just
have the letters match. Yes.
Yeah. Oh, that's right. I'm sorry. Exactly. So yeah.
You delete some of these edges.
Yeah. No. You don't delete the edges. It's just that if the edge, I should have said, if you are at a place where the final two symbols match, then you can do this step at cost 0. Otherwise, you pay 1. So the only place that the input matters is the costs on the diagonal edges are either 0 or 1. Yeah, that was really important. Thank you for that.
Otherwise, we know the distance in this.
Right. Okay. Very good. Yeah, so I'll just remind you, right? So if you want to solve shortest path in a graph problems, then the running time is proportional to the number of edges of the graph. So here there's n squared edges, and that's how you get the n squared. One way of interpreting what the n squared algorithm is. Okay.
So are you solving this abstract problem? You are just given this graph, and there are just labels 0, 1 on the diagonal edges? Probably not. This is too general.
It's too general.
It's too general. So
Yeah.
you need structure of it's coming from
Yeah.
two words.
Yeah, although, I mean, there is a question about it. I mean, like one of the open questions is how general, can one adapt what we're doing? Right now, it is using particular properties, but
Possible you think that this problem has a subquadratic algorithm, approximating the distance in this graph?
yeah, I mean, depends on what kinds of, I mean, under what, you could ask, under what restrictions on the weights?
But the most general restriction is no restriction. It's 0, 1 on diagonal edges.
Well, I mean, you could imagine,
I'm just asking the most general question.
no, that's not even the most general. The most general is arbitrary weights on the edges.
No, I understand, but
Oh.
the most general that's relevant to this is
Yeah.
and
But even, there are ones relevant to this in the sense that you could look at edit distance where you assign different costs for different substitutions, different deletions, and that would lead to different weights. That problem, I actually think, we haven't thought about it, but I actually think there's a reasonable chance that that can be handled by something similar to what we do. Okay. All right, so we are switching.
No.
Oh.
We need lights.
Well, there's lights
There
back.
will be more lights.
Are there lights more? I just realized that I forgot I have some notes which I want to refer to occasionally. Okay. All right, so I want to make use of that graph and the geometric picture of this graph. Okay, so the first thing I want to do is just describe to you sort of just a completely general paradigm for how you could approach this problem. And if you think about the problem for very long, it's, at least if you think of it from a combinatorial point of view, it's kind of the only thing that you can do. I will mention that, for example, the Andoni, Krauthammer-Onak paper uses this kind of metric embedding approach that they come up with another metric on strings which they analyze that metric and they find an algorithm, and then they show that that metric is within a polylog factor of the actual metric. And that's where that comes from. But so theirs does not follow what I'm about to say, but okay. So here's the way I want you to think about the algorithm. What the algorithm is going to do is somehow identify certain pairs of substrings. So again, you should think of x as going along here. You think of y. And I index an interval, a horizontal interval by capital I, and typically a vertical interval by capital J. And what it's going to do is pick a bunch of these pairs ij and come up with somehow an upper bound on the edit distance between this substring and this substring. Okay? And it's going to do this for a bunch of pairs. Okay? And it's going to pick these pairs in some way, and that's okay. Then it collects them. So it's going to build, so we call these things certified rectangles. Here's I cross J. And then it's, I write it as I cross J kappa. And this is a distance upper bound. So kappa is an upper bound on the edit distance of xi yj.
So we should have theta in the back of our minds or not?
Not for the moment. Not for the moment.
Not for the moment.
You'll see.
We want good upper bounds of that.
That's right. That's right. And now you collect these certified rectangles. And that's phase one, is collect a bunch of certified rectangles. Okay. And phase two is process the certified rectangles. Okay. So each certified rectangle is an upper bound on the subpath. What's the optimal subpath from this point to this point? Doesn't have to, you know, it goes like this. Okay. So you're getting, for certain sub problems, you get some upper bounds. And then you want to piece them together. Okay. Now, you can take all those upper bounds and piece them together just using the standard shortest path algorithm. You can imagine introducing shortcut edges where you put that, and then you just ask what's the shortest path. So the second phase just processes that information. An important thing is that when you find one shortcut, it actually implies some other shortcuts. Namely, if I find a shortcut from this point to this point, and I know I have an upper bound of kappa, well, if I move this point up here by 2 steps, and I look from, then I also know that this distance is at most kappa plus 2. I can distort the rectangle, and that changes the distance bound by the amount that you distort. So those are kind of implicit. And now the second phase algorithm wants to take all this information and all the applied information and find the best bound that it can. And what I will say is that part is actually pretty routine. The important thing is that the algorithm, so if you take the original graph where for all the diagonals you put 1. So you imagine that's kind of the naive upper bound on everything. You just put 1 on every edge. Okay. Of course, the shortest path has length n in that graph. So, okay. Now I add these shortcut edges. And now I ask, what's the shortest path in this new graph? The original graph with all edges 1 plus these shortcuts. And what's the shortest path there? And then it is a relatively easy exercise in let's say, first-year graduate data structures to show that you can actually solve this shortest path problem in time proportional to the number of shortcut edges, as opposed to the number of total edges. So even though you've got all these edges of length 1 in the graph, you can actually calculate this thing in time proportional to the shortcut edges. And if we have time, and if people care, I can show you that later. But this is really, in the paper, this is, less than 1 column to describe to describe that. And it's just standard tricks. You pay a couple of log factors. You have to do some sorting of vertices as you go. You kind of process things from left to right, and you do kind of standard algorithms tricks. No, so now, I mean, the choice of the rectangles is, so what I want to point out is that the choice of the rectangles is really the main thing, okay? So what you should view your objective is that it's just to produce a bunch of rectangles which somehow capture the most important information about the shortest path. Now, what would that mean? Okay. So what would it mean that the rectangles you found capture? So there is some unknown shortest path in this graph. Goes something like this. Okay. Now, here's something that, do the following thought experiment. Let's divide this thing up into segments. I'll call these segments W. And later on, my segments, I will have two different segment lengths, W1 and W2. But right now, let's call them W. And imagine this, here's this unknown shortest path. We don't know it. But now cover this shortest path by rectangles in the following way, where what you do is you identify for each of these breakpoints where it intersects the path, and then just cover it. Okay. Now, if I am clairvoyant and I know where these breakpoints are, then if for each of these rectangles I get an upper bound, those upper bounds will be enough because that's all I need. So all I need is a set of upper bounds, one for, and if those upper bounds are reasonably good, I mean, I could, if I actually knew these breakpoints, I could actually calculate the shortest path for this, the shortest path for this. Okay, and I could just run the exact algorithm, in fact, and the cost of running the exact algorithm is the product of this length times this length. And what you'll see is that the overall cost will be W. The cost of calculating the exact edit distance of all these boxes, if I knew where they were, would just be order n times W. Because it's W times this height, W times this height, and those heights add up to n. Okay. Now, another thing you notice, because of what we said, I don't actually have to guess these breakpoints exactly. If I guess them approximately, because as long as the error in my approximation of guessing, and that's where the theta is going to come in. So I can afford an error of theta, essentially, when I have this particular theta that I have in mind. So I'm now trying to tell the difference between edit distance theta n and 1,000 theta n. And so I can afford to introduce error on the order of theta n. So if I perturb these things by a small amount, then the estimates I get will introduce some error, but as long as I control the total error. All right. Okay, so what you should view now is our objective is to choose our rectangles in a way that even though we don't know the path, we somehow are guaranteed to get enough rectangles that we will approximately cover the path in this way. So it's like I need my good rectangles to sort of approximately cover the path, or to approximate this sequence of rectangles. All right. So what's a naive way to approach it? Completely naive way to approach it is, let me mention one other thing. It's actually sufficient when I'm looking for rectangles just to restrict myself to squares. Okay. Now you say, well, wait, if I restrict myself to a square here, don't I introduce a lot of error? And the answer is yes. But if you have a piece of your path which has a much higher vertical thing than horizontal, or the other way around, then the edit distance that this represents is already very expensive, because for any pair of sequences that are very imbalanced, the edit distance between them is at least the difference between their lengths. Okay, so yes, it's true that this thing does not approximate this very well, but this thing is already very expensive, so paying a factor of 2 or something, which is what we would pay if we shrink to a square, is not very much. So the only things that we have to approximate really well are things which are approximately squares. But the problem is, maybe this thing behaves exactly the way I said, which is it starts with with imbalance, and then it's a bunch of squares. But we don't know where those squares are. We don't, maybe they're down here, maybe, right? So that's the issue. Okay, so what we're going to do is look for a bunch of squares now. That's all we're looking to look for. And we want these squares to reasonably cover this path in this sense. Okay, so here's a naive way to do it. For every w, let's look at I could look at every possible interval of length w here and just compute the exact edit distance. That's very expensive. That means I'm going to do w times n edit distance computations. I will do, for each of these intervals, I will do n edit distance computations. That edit distance computation costs w squared. And I have n over w intervals that I have to deal with. And so the total cost of all that is n squared times w. Well, that's terrible. But that'll do it, but it's terrible. Okay, so I can do something slightly less stupid, which is I don't have to look at every interval here. I can look at intervals that are spaced theta n apart. Theta being the tolerance that theta, okay. So, sorry, not theta n apart, theta w apart. Okay, so what I want to do is I want to introduce at most theta w error due to, the perturbation. So I want the granularity of my grid to be theta w. If I do that, then instead of having n different intervals, I'm only going to be considering n over theta w intervals. And that improves this. It at least gets rid of this w. But it's still worse than n squared. Okay, theta is less than 1. Okay, everybody with me so far? So this granularity, I just want to emphasize, I said this a little badly. The reason for this granularity theta w, one thing I could also do, but this is not good enough, is I could just similarly divide it vertically into strips of size w. Then I would have n over w. But that's not going to be good enough because, maybe things are shifted halfway up, right? So I'm going to be off on all of them. So that's why I have to introduce, instead of just these intervals of length w, I have to look at shifts of them by this theta w. And that's where we get that. Okay? Okay, so this is the naive algorithm, the naive approximation algorithm. Its running time is worse. Okay, so how are we going to improve the naive algorithm? Okay, so there are two ideas.
Now you didn't use it.
Oh, I did use, well, no, not to choose the rectangles. Not to choose the rectangles, that's right. That's right. So there are two possible things you can try to do. If you have an algorithm, and you could say, well, I could try to reduce the total number of rectangles I look at, right? The total number of rectangles I looked at was n squared over theta w squared. And I paid for each one, I paid a cost of w squared to analyze it. So I could try to reduce the total number of rectangles I look at. Or, well, you know, I can't reduce this cost because that's the problem I'm trying to solve. But amortized, that's right. So maybe I could simultaneously solve a bunch of these. You know, I get a bunch of instances that I have to solve or approximate, and I could maybe simultaneously solve a bunch of them at amortized cost less than w squared.
And the reason is that the information in the input is just linear length. Well, this is
That's right, that's right, that's right. And if you look at this, you know, here I am solving, I have all of these intervals and I have a bunch of intervals, and I want to solve a whole bunch of problems which are, you know, this substring versus this substring and all possibilities. And maybe I can, you know, do something which uses the work that I did in one of the instances to, okay. So what we're going to have is a technique which sort of does one thing sometimes. So it's going to reduce, in some cases, it will reduce the number of rectangles. And in some cases, it will reduce the amortized cost. All right, and it's the combined thing that's going to give us the algorithm. So let me explain how you might hope to reduce the amortized cost. So let me take an interval here. And suppose it has the property. You know, I want to compare this to this, but instead of doing that, I'm going to start by comparing this guy to the guys down here, to other intervals down here. And suppose it has the property that it's close to a lot of intervals down here. So you can find, you know, an I prime and an I double prime. And the edit distance between these is close. Well, now I compare this guy to all these intervals here, just this guy. And I get bounds on the distance between this guy and this guy. In fact, I get well, since all these guys are close, triangle inequality automatically gives me upper bounds on these guys and on these guys. Okay. So suddenly I've leveraged, so I have only done a linear number of edit distance computations, but I get approximations on a quadratic number of rectangles. Okay. And that's great. So, and in fact, you know, you can do that. And now the only catch is, well, what happens if this guy isn't close to very many guys?
There is also the other thing is comparing these pairs. You need to know that you need to compute the distance between these pairs.
Right, but what I'm saying is I take I, so we'll see. Okay, in fact, let me describe, now let me actually state an algorithm, okay? So I'm going to state sort of one of the main routines, but there's going to be one little black box in that thing. Okay. So I need a little bit of notation. So script IW equals the partition of 1 through n into pieces of size w. And let's say IW theta equals the set of intervals with W starting at a multiple of theta W. So you should think of IW as the intervals that we care about along the horizontal, and IW theta is a larger set of intervals, which includes this one, but it's these more precise shifts. Okay.
So it's okay to think of theta as a constant, like 1/100.
Yeah, that's right. Yeah, in fact, let me tell you, just for the purpose of this thing, and I noticed, so this is exactly what happened last time I gave this talk. I'm a little too leisurely. It's 12 o'clock, so we go till?
Let's say most 12.
Okay, I'll stay within that. Okay, all right. So let's actually pick some particular parameters which you can have in mind. So theta is going to be n to the minus 0.05. And I'm going to have a W1 and W2. This is n to the 0.1. This is n to the 0.3. And there's going to be one other parameter, d, which is n to the 0.2. Okay. Now, our real algorithm is going to optimize these parameters. But I just want to give you these specific parameters so you can sort of, we can follow it and see how the subquadratic time emerges. So right now I only have W, but think W eventually is going to be W1. We're just going to need another later on in the algorithm. Okay, so here's an algorithm. You start, I'm going to let T, so before I do that, one other thing I want to say is that the algorithm will search for boxes of distance less than or equal to epsilon I equal 2 to the minus I for I equal 0 to log n. So when we're running the algorithm, you should think of, we have a particular distance bound, and we're trying to find boxes that are within that distance bound. We're going to eventually do this log n times for different distance bounds.
But relative distance to W.
This is relative distance, yes, of relative distance. So normalized distance. Okay. Okay, so, given epsilon I, so here's the algorithm. We're going to start by letting T gets IW. So those are the horizontal candidates, intervals, that I care about. And so here's the black box, which I will get to a little later. But you'll see it's a simple black box, but I don't want to unpack it yet. So we're going to choose, while T is non-empty, choose I and T. And test I. So test, I'm going to tell you what test is later. It's some test, and the test either declare I dense or sparse. That's what the test does. And if I is sparse, whatever that means, sparse, by the way, well, dense will correspond to the case where I has lots of things that are close to it along the horizontal, and sparse. So if I is sparse, then you're just going to abandon I. So if I is sparse, so you have S, which is the set of, I should have initialized S as empty. So S equals S union I, and T equals T minus I. So else I is dense. And now what we're going to do, so this is like a comment, use I as a pivot. Pivot is just a term that we use for this. And what it means is you're going to compute the distance from I to everybody else, every horizontal interval and every vertical interval. So compute the edit distance from xi to xi prime for all I prime in IW, or sorry, in T, which is the remaining set, and the edit distance from xi to yj for all j in IW theta. And now what we want to do when we do those computations is just to capture the guys. So now so everybody is within 3 epsilon I. You'll see there's a particular constants here which we'll put, and let x be the I primes in T such that the edit distance from xi okay. And now for all I prime in x, j in y, certify the box I prime cross j with distance upper bound 5 epsilon I. Okay, so the fact that this is 5 epsilon I is just triangle inequality, so that's okay. You'll see in a minute why 3 and 2. And it's just a convenient thing that we'll see in a moment. Okay, so that's the whole algorithm. Okay, so what does this algorithm end up doing? Well, it sort of identifies these intervals which we called sparse, and we put them aside. Okay, and everybody else, well, we do this, we find these 2 sets, and then we get a bunch of boxes.
When you say you put them aside, you need to compute for them edit distances also.
Later.
So
Yeah.
it's not the whole algorithm.
That's not the whole algorithm.
Eventually you're going to certify all the possible boxes, but some...
Not all possible boxes, you'll see.
Okay,
You'll see what we'll do.
This is just saving you time because...
Yeah, that's right.
Because of the density.
That's right. So, but let me do, so let's just see, so I want to analyze a couple of things. How long does this thing take, this algorithm take? Now, if we are lucky, then the set S is empty. And then I claim that we're actually done, right? We have all the boxes we need because what we've done is so let me make a couple of claims. So claim for all I not in S, So if I isn't in S, then and for all j such that, let me call it I prime just to match that, and for all j such that the edit distance xi prime yj is less than or equal to epsilon I, we have certified xi prime yj, or I prime cross j with distance at most 5 epsilon I.
Don't you need to add theta? Don't you need to add theta to this?
Why? It doesn't come in. It's just for all, we're only paying attention to those intervals.
These are the intervals. They are defined by shifts of theta.
Yeah. We've already restricted to the ones that are specified. So then, so now why is that? So I want to say, well, that's obvious if I prime was the pivot. But I prime might be in the set X. Okay, but what do we know? So this is just a simple metric space picture, right? Here was I that we used as a pivot. And I prime is some arbitrary guy that's distance at most 2 epsilon I from here. Now I want to make sure that I certify everybody who's close to I prime within epsilon I. So that's some ball here, but anybody who's within epsilon I of I is within 3 epsilon I. I mean, if he's within epsilon I of this guy, he's within 3 epsilon I of this guy. And that is one of the guys we put in script Y. So we've taken care of everybody except the guys that we ended up putting in S. And by taking care of, I mean that for every box that's close, we've gotten a good estimate for it. And we do this for all for log n different epsilon i's, and we're happy. Okay, the other claim is that the runtime, well, let's say, what's the running time of this algorithm? Well, how long does it take to process a pivot? Okay. Well, I run this test algorithm, which I haven't told you what it is yet, but we'll do it. We'll see. Let's ignore that for the moment. So I'm going to, when I use I as a pivot, oh, sorry. I guess I do have to use I have to tell, before I analyze runtime, I should tell you what is test. Okay, well, the test is just the most naive thing you do. So what I would like to do is I only want to declare I dense if it has enough, if there are enough guys that are within epsilon I from it along the horizontal axis. And what's enough? Enough is this parameter D here. Okay, so test determines approximately, does I have at least D close I prime, and close is within epsilon I.
Yeah, D times N.
D times, no, just D. This is just D.
Oh, N to the point 2. Sorry, it's a number. Yeah,
Yeah, it's a number. Okay.
that's what it's like.
So how do you do that?
By some
Sample, right? So I just sample a 1 over D fraction, or log n over D fraction, okay? So what is the cost of test? Well, I have to look at a 1 over D fraction of the intervals. I'm throwing away log factors. Okay, so there are n over W horizontal intervals. I divide it by D. So that's the number I'm sampling. And for each one, I have to do an edit distance computation. So it's n over W. which is n w over d. Okay, and then how many times am I going to do this? Well, I might do it for every horizontal interval in worst case. So I'm going to do it n over w times. Okay, so that's like n squared over d. And I'm suspicious if I did this right. Sorry, I feel like, did I cheat you? These people see, does that look right? I feel like just the expression doesn't look right to me. Okay, I'm sorry. Yeah. So it turns out, for technical reasons, I didn't tell you the right test. This is the test that we originally started with, but it turns out it's better to switch to, instead of comparing I, when I test I, instead of seeing whether there are enough D close horizontal guys, I want to look for D close vertical guys. So D close J such that, you know, the edit distance of xi to yj is less than epsilon I. All right, so that's slightly different than what we set up. We were looking for this guy that has lots of horizontal close guys. It turns out that it's, for technical reasons, and you'll see that things work out better if you look for somebody with lots of vertical guys. Which, you know, you might think, well, does that actually serve the purpose that we want? Which was because maybe he has only a few close horizontal guys, in which case I don't actually certify that many boxes. But you'll see that this works out. Okay, so now the cost of test is what? There's another theta down here, and that's what I was missing. Okay. Yeah. Okay. Okay, but we chose, if you look at the parameters, this is like n to the 1.85 for the particular choice of parameters. So we can do all the tests we need to do. And the important thing is, right, that this d times theta has to be bigger than 1, significantly bigger than 1. Okay. All right. So now, so I'm analyzing the cost of the algorithm. All the test operations was this, and now the cost of processing the pivots. Well, for each pivot, cost of a pivot, well, you compare the pivot to all the horizontal and all the vertical. That's n over theta w. And you do an edit distance computation, which is w squared. And that's it, right? That's the cost of processing a pivot. So that is n over theta w. Okay. Now, how many pivots do I process? Well, I was hoping to say something like at most n over d pivots. But under the new definition, that's not entirely clear. But the new definition has the following nice property. Okay, so here's a claim. If I and I prime are distinct pivots, then the set of epsilon I close j's for I is disjoint from the set for I prime.
These are distinct pivots, or dense pivots.
No, pivot must be dense, right? So something is only chosen as a pivot after it's declared dense. So what's the point? We have the picture that we have an I, and we chose it as a pivot, which meant there were lots of j's that are within epsilon I of it. J1, J2, and these are all within epsilon I. And now we have an I prime, which also becomes a pivot. And I want to claim that the things that are close to I prime can't be any of these. Why?
Triangle inequality.
Yeah, because when we processed I, we found everybody who was within 2 epsilon I of I, right? And if this guy was within epsilon I of one of these, and this guy, then he would have been within 2 epsilon I, and that was somebody that we would have put in X. So what that means is that for each of these guys, the set of guys of their neighbors is disjoint. And there are D of them, because that's how what test does. So we have disjoint sets of size D. How many can there be? So that means that the number of pivots is less than or equal to n over theta w d. Okay, and you multiply that by the cost of processing, so cost of all pivots is n over the product of these two, which is n over theta squared d. Okay, and again, so we need this to be, the denominator to be big, n squared. And d was n to the 0.2, I said, and this was n to the minus 0.05. So you still get like an n to the 1.9 in that example. Okay, so now I have 6 minutes to tell you, what do we do with the sparse guys? Right? So again, just to recap, we tested every interval. We go through, we tested, is it sparse, is it dense? If it's got lots, if it's dense, we pivot on it and we do this. And at the end, we have collected the sparse guys. Okay. So I want to look at the picture. W now becomes the parameter W1. That's n to the 0.1. But I also have a W2. So now I partition this thing now into pieces of size W2, which you should think of as n to the 0.3. And each of these has a subpartition into n to the 0.1. Okay? Now, let me now process each of these intervals one at a time.
What's the idea?
What?
What's the idea?
Oh, what's the idea? So the idea is going to be this. I am now going to, so either when if you think of this interval, this W2 interval, either, let's say, all or almost all of these guys were dense and there were very few sparse. And then the boxes that I got here will, this W2 box, there is some box here that I'm looking for. Okay, but if everybody here was dense, then those little boxes will give me a good estimate for this. Why would I not get a good estimate for this piece of the, let's go to a middle piece. So again, this is subpartitioned. If every one of these guys was dense or none of them are sparse, then all the information I got will be good enough to get a good estimate for that subbox. So what could go wrong? Well, a lot of these guys were sparse. Now, there is something but I won't be able to say all the details, but because there's this thing about, we're doing this for different epsilon i's. So right now we're just focusing on one epsilon I, but that's okay. All right. So there might have been a bunch of sparse guys. So now what I'm going to do is I'm going to now directly look for boxes of width W2. So for this guy who has lots of sparse guys, or at least maybe even at one sparse guy, I'm going to do the following thing. I'm going to try to use the sparse guys to guide me to find the box that this guy gets matched to. And I'll do it this way. It's very simple. So I'm just going to randomly sample a polylogarithmic number of sparse guys. There may be they may be all sparse, but I randomly sample a polylogarithmic number of sparse guys. And for each guy I sample, what I know is he only has a small number of things that are close. He failed the test. So I exhaustively find for everybody I sampled the guys that are close. And that gives me a little box here for each close guy, but not too many boxes, only D of them. And for each of those, we do what's called the diagonal extension of the box. Just take the box and extend it to that. So how many boxes do I generate this way? Only D boxes times polylog. For each of these guys, I generate D boxes. And for each of those boxes, I just exhaustively compute the distance. Now notice that if I had tried to do this for this guy has n over theta W2 candidates that he might be matched to. But now I have restricted the set of candidates to just D times polylog. Okay, so now you can write down what the cost is. Now the question is, why does that work? Okay, so now the claim is that these sparse guys will help you identify, they will zero in on a box. Okay, so why is that? Well, let's look at the box that you're really trying to zero in on. That's some square box which, closely covers this path. And you have these intervals which were identified as sparse. And each of those has a cost inside this path. So there are two possibilities. If these intervals, which were sparse, have a very high cost inside this path, then they don't matter. Because if I just use the information that I found from the dense guys, these guys are expensive anyway, so they don't. So even if I use the worst possible estimate for these, I will get a good estimate for this. So the only reason why I need these guys is because a lot of them have a small cost here. But if they have any guy that has a small cost in here, means in particular that this process of finding the guys that are close will include this segment. And then when I take the diagonal extension, diagonal extension may not be exactly this box, so you have to prove a lemma which says that the diagonal extension is a reasonably good estimate to the box you're looking for, good enough that it doesn't introduce much error. Okay, that's it.